Okie dokie. Today we are doing the natural exponential function.
We only have one problem and then we're done.
What?
Function.
Well, it's technically one function used in multiple ways.
It's very misleading.
I know. Maybe that was intentional. Okay, so we're doing the natural exponential function. Before we get into that, I would like to review a compound interest problem from yesterday, just so I know that we know how to do it, since we didn't get to spend a whole lot of time on it. So let's say that I have $1,000 being invested into an account at 9% interest. And I would like to know what is the new amount in the account after 1 year. If the interest compounds, I don't know, let's say monthly. Start there. So this is actually the same problem that we had on our notes yesterday, but we are going to expand upon it. So if I have a compound interest problem, what equation am I going to be using to solve it? Somebody tell me what it is. A equals, they'll give me the generic one first. R over N to the NT power, right? That is our compound interest formula. It works every single time. All we have to do once we get this is fill in the P, R, N, and T, right? My principal amount is $1,000 because that's how much I'm investing. My interest rate is 9%, which I write as the decimal 0.09. T is 1 because I want to know how much is in the account after 1 year. What's my N value stand for?
Like the number of times it compounds.
The number of times it compounds per year. So how often am I taking the interest? Monthly, which means there are how many times I'm taking interest in 1 year? 12, because there are 12 months in a year. So my N value here is 12. And I would just plug all of that information into that equation and solve it out, right? So let's do that. Just so I make sure we can all do it. So I have 1,000 times the quantity 1 plus 0.09 over 12, all taken to the 12th power. If you're plugging this into your calculator, you need to do it in steps, or you need to be extremely careful with your parentheses. I always suggest steps. So I would do this part first, putting this in parentheses. I would take that answer and raise it to the 12 times 1 power, and I would multiply that answer by 1,000. That is the sure way to make sure you don't mess up on this. So everybody do that. I want you all to plug it into your calculators. I want you to solve it out and make sure we get the correct answer.
Oh.
No.
B.
No.
Do exactly that, I'll tell you.
Do it again. In steps. Anybody have an answer they seem pretty confident about? Jojo, do you not have a calculator? What is on this wall next to me?
Calculator.
A whole lot of calculators. Yes, Molly.
1,093.8.
Okay, I would say 0.81, but yes. So $1,093.81. Anybody else getting that?
Oh, I messed up.
Anybody not getting that? If you did not get that, I want you to turn to your neighbor and compare calculator process, okay? Because I know Gunner's not getting it, so somebody needs to check in with
I
him.
didn't even finish the second time.
You good, Becca?
Yeah.
Okay.
Yeah, the bomb.
Your tire, what? That's disgusting. Okay, are we figuring it out? Do we see the mistake that we made when we plugged it in?
It took me so long to figure out how to do a fraction on the graphic calculator.
You could just do parentheses number divided by number.
Oh, well, I didn't do that.
Or you can insert a fraction, that's okay too. That just takes way more work.
But I figured it out.
Okay, boys, let me see this. Yep, I'm ready to watch. Okay,
Right.
okay,
Right.
yep. Okay.
That.
Oh,
Yeah.
Oh my gosh. Of course I did that.
okay. Anybody else not sure about what they did to get the right answer, or did they not get the right answer? What? Sorry. Okay. While I'm helping him, what if I said I wanted to compound the interest daily? Find out what my answer would be.
No.
Yes. So you would do zero, and then okay. We call that a carrot, by the way. I don't see you guys working.
What are we supposed to do?
What if I wanted to compound the interest every single day? I would like you to find out the amount I would have after 1 year if I took interest every day.
Oh.
If I'm taking interest every day, what's my end value? 365. Let's just assume it's, whole numbers. Do you feel confident in your answer?
No,
Okay, what'd you get?
1,094.16.
$1,094.16. Everybody else coming to that same answer?
35.
Say that again. 1,000 what?
$1,094.16. So you should have 1094.16 roughly. Oh, Gunner. Oh, Gunner.
Yeah.
Wow.
I cleared it.
I can go back up and see. Good try though.
Oh, yeah.
Oh, it's no longer to 12, it's to 30.
Oh my God.
That has to change as well.
Are you serious?
Yeah,
This is insane.
let's make sure that when you plug this in, you're changing the N here and you're changing the N here. Okay, both of those 12s need to become 365. What then would I plug in for N if I wanted to calculate the interest hourly? What would I have to find out? How many hours are in a year, right? Which isn't that bad, 365 days times 24 hours and you'd get some number. But then what if I wanted to take it a step further and calculate my interest every minute? I would have to figure out how many minutes are in a year as well. And then I could go even farther and find out how many, or if I wanted to calculate it every second, I would have to figure out how many seconds are in a year as well. So all of this gets really, really repetitive and really, really big numbers. So the likelihood of you making a mistake is exponentially larger. So they came up with the natural exponential function. This allows us to continuously calculate changes every second of every minute. Okay? I know, right? So it saves you from having to do this each time, and come up with like thousands and thousands, because there are 525,600 minutes in a year, just so you know. So it does take a hot second to do that. This natural exponential function,
It's like a very small number.
That's a good
it seems very small, but it's actually not.
Mr. Ryan, that was a good lead-in.
Thank you. This natural exponential function is our base e. So I know we talked about it a little bit yesterday. E is an irrational number, just like pi. So we use the letter e to stand for that irrational number, because I can't just keep plugging it in every single time. The cool thing is you actually have an e button on your calculator that does the math for you, just like you have a pi button. The way that this e is used in a compound interest problem is it creates an entirely new formula called PERT. It still uses all of the same information, except for the n value goes away because I'm compounding continuously with that natural exponential function e. So if I wanted to compound continuously, my p is still my principal, my r is still my interest rate as a decimal, and my t is still the amount of time that I'm letting it sit in this account, or letting it grow or decay in interest. And then I would just plug it directly into my calculator and get my answer, just like on the previous problem. I actually think this one's a little bit easier. So using the same information from the previous problem, assuming my interest is compounded continuously, I would like to find out how much money I have in that account after a year. So from the previous problem, what was my principal amount? 1,000. What was my interest rate? 0.09. And how many years am I letting it sit for? Just like before, I suggest you do the e to the power of 0.09 times 1 first, and then multiply your answer by 1,000.
Where is the e in?
It is by your natural log. It should be on the left-hand side. It might even be in blue or green.
I didn't know that.
What is EE?
2.781 something rather. Yeah, that one. Yep. If you can't find your E, it is with the natural log button usually, because they're natural inverses of each other. So you'd have to hit second, and then you'd hit the LN button. Did you find it, Marissa?
2 E's I see.
They're the one on the left-hand side with the LN button. It's in blue. No, don't put the letter E. That's completely different.
No, there's an E on the division.
Why is it different?
Because that's like a letter for typing kind of E, not a base E. See, that's a letter. Okay, what was our answer when we did this?
37.268.
Not.
1,094.
$1,094.17. So we actually got really, really close when we calculated if we compounded interest each day. But it still wasn't close enough. Okay, did anybody have major issues plugging the E into your calculator? None at all. We're okay.
Wait, in the first equation,
Yes.
never mind.
Okay. So let's go ahead and practice the E again with another application problem that is compound interest. Because you really can never do it enough.
You can.
No, you can't. Okay, so let's suppose that $20,000 is deposited into an account. That pays 6% interest. Compounded continuously.
What is continuously supposed to be?
That's the E. Whenever you see the word continuously, That means I'm going to use the E, so PERT, instead of that compound interest formula we did yesterday. That's always your keyword. I always remember it as PERT, sorry. How much money would I have after 5 years in this account? That's what I would like to figure out. So clearly I'm going to be using PERT because it says the word continuously in here, which means it's a natural exponential function. I still have to identify my principal amount, my interest rate, and the amount of time I'm letting the money be in the account and accrue interest. So what is my principal amount here? 20,000. That's how much money I'm initially investing into the account. What is my interest rate? 6%, which we write as 0.06. And Jojo, how long am I letting the money sit in the account? How long did I say? 5 years. Continuously is how often it's compounding interest. We still have to give an amount of time that it's going to sit in there. Okay, so I did say for 5 years. So T here is going to be 5. I take all of this and I plug it into that PERT equation. So when I do, I get 20,000 e to the 0.06 times 5, and I plug that into my calculator. All of you do that, please. It's really good practice. Right? I'm a comedian. When somebody has an answer they feel confident about, raise your hand. Molly, what's your answer?
$26,997.
Yes. $26,997.18. Did anybody not get that when you plugged it into your calculator? Anybody confused about how to plug it into your calculator? Okay. You guys are insane. There is another example in here that if we have time at the end, I'd like to come back to, but it's not super important. You should look at it, however, at some point when you have time. And it's just about plugging it into your calculator and finding intersection points that way. It's not super duper important. So the next example, or the next thing I'd like to talk about is the law of growth and decay. So yesterday, whenever we had an exponential function, it was pretty much always either a growth exponential function or a decay. The same thing still kind of applies here with our natural exponential function, except our growth or decay is decided not by our base, but by our rate. So if it's a growth function, my R value is going to be positive. So if it said it was growing by 6%, my R value would be a positive 0.06. If, however, it said that my value was decaying, I would use the negative of whatever the percentage is. So my R value is going to be less than 0. If I said I was decaying by 6%, in this problem, I would use negative 0.06. So we just apply the negative in front of our decimal if it's a decay, and if it's growth, we keep it positive. Of course, that's more formally written in your notes, but who needs that? So of course, we're going to do 3 more examples that will be both growth and decay, so you can kind of see what I'm talking about and how that works. So the next example I would like to look at is a population example. So I'm just going to read it out loud, and then we are going to write the important information. So it says, predicting the population of a city. The population of a city in 1970 was 153,800 people. Assuming that the population increases continuously, that continuously right there tells me I'm using E in here somewhere, at a rate of 5% per year. Using this information, predict the population of the city in the year 2020, so this year.
Oh.
So I need to start with the population at the start of this model. Okay, so that told me in 1970, the population was 153,800 people. From this initial population, was my population increasing or decreasing? Increasing, because it said it grows. And it told me it grew, at a rate of 5% per year. So the final question, the one I need to answer, is what is the population in the year 2020? It said continuously in there, so I know I'm using PERT. For the PERT model to work, I have to know the principal amount, which I do. That's the 153,800. I have to know the rate at which this is growing or decaying, and I do. That's 5% per year. And I have to know the amount of time that I'm allowing this model to grow or decay before I calculate. Do I know that? It didn't explicitly tell me how many years I was waiting to check the population, but it did give me years so I can calculate it myself. If I knew the population in 1970 and I want to know the population in 2020, I need to figure out how many years passed between 1970 and 2020. So if you don't know that off the top of your head, you can do 2020 minus 1970, and you will get time equals what? 50 years.
13.
50. Nice try though.
So close.
So now I have all this information that I can go ahead and plug into this model. So when I do, I get A equals 153,800 times E to the 0.05 times 50. And I would like for you to plug that into your calculator. It is going to be a large number.
Like millions?
It will be above 1 million. You already did it?
I said, no, I don't think I will. She gave me like
Got it. I'm going to give everybody a chance to plug this in.
Would you round up to the nearest whole number?
Since we're talking about people, I would approximate it to the nearest whole number, yes.
So if it's like 5 or 6, just round up.
We can't have a part of a person, so we typically round to whole numbers when we talk about population. So what answer did I get for my population in 2020?
873,668.
Since I rounded, I do the curved equal sign, which means approximately. So my population is approximately 1,873,668 people.
Dang.
I heard that.
Okay, we're gonna have to add some
Deaths.
That brings up a really good point, though. Does this guarantee that after 50 years, I'm going to have 1.8 million people in this town?
No, just use your head
No.
at least.
This is just assuming that the trend that we noticed in 1970 continues at a constant rate. Of course, there are other factors that contribute to population, such as birth rates and death rates and, COVID. So you would have to take into account that this is an approximation, not a guaranteed value. Okay, anytime we're doing something like this, it's an approximation assuming all the variables stay constant.
Yikes.
Any questions on this model specifically? Okay, so now let's do a decay model with plutonium.
What?
Okay, so I'm gonna go ahead and read it, and then we will pull out the important information. It says the isotope plutonium-238 is used in powering spacecraft and decays at a rate of about 0.79% per year. To the nearest tenth of a gram, how much of a 100 gram sample will remain in 88 years? A lot going on there. So in order to use this, I know I'm going to be using that PERT model because it's got to be constantly decaying. It doesn't just wait a year and then suddenly knock off a chunk of the population I started with. So I have to know how much I'm starting with. I have to know the rate at which it's growing or decaying. And I have to know the amount of time that I'm letting it sit before I calculate, correct? Okay. How much of this plutonium was I starting with? Anybody catch that? 100 grams. So my principal amount is 100. Is my plutonium stash growing or getting smaller? Decaying, which indicates that my interest rate is going to be negative. Remember, whenever we decay on a continuously compounded problem, it's a negative R value. So it told me it was 0.79%, which means to find the decimal, I need to take this decimal place and move it 2 places to the left, which means the decimal version of that is 0.0079. So it's negative 0.0079 as my interest rate. And then how long am I waiting to calculate the plutonium mass at?
Like 80 years.
88 years. So having all of this information, I go ahead and I plug it all into my PERT model. So when I do, I get 100 times e to the negative 0.0079 times 88. And then I plug that into my calculator. Once you think you have an answer, just pause, check with your neighbor, see if you guys got the same thing. Ray, do you feel confident in your answer? Okay, so Ray calculated this. Oh, that's not how you write that. And got approximately 49.9 grams left after 88 years. Anybody else get that?
Yes.
What is 49.9 really, really close to? 50. And what do we notice about 50 in comparison to the 100 grams we started with? So I could even take a leap and say the half-life of this plutonium isotope is approximately 88 years. Because after 88 years, the amount I started with was cut in half, roughly. Okay, so 49.9 was entirely correct, and it did lead me to generalize the half-life of this isotope. So there's more information than just the answer that you can pull out of these sometimes. Any questions on that one?
We go home.
No, we have one more. Anybody super confused by what's happening here? Fantastic. So our last example, because I know you're all just ready to be done with this.
It's gonna be bad.
Nap time.
Hilarious.
I know, right?
Finding the zeros.
Okay, so let's assume I have a natural logarithmic function. That is x squared times the quantity negative 2e to the negative 2x
Oh no.
plus 2x e to the negative 2x. I would like to find the zeros for this function.
Can we just skip it?
No.
That's what I do with test.
I don't know.
You're gonna be probably like this on the homework.
Is there homework tonight?
There's homework tonight. I know this looks extremely scary. It's just like every other problem that we've done. So the first thing I need to do is I need to put everything together. So I need to multiply this x squared in. Then I'm gonna look for a common factor that I can pull out. And then once it's factored, I'm gonna set all my factors equal to 0 and find the zeros, right? That's just how it works. So the first thing I wanna do is multiply this x squared into that term. This is all one term, so when I multiply it in, it just becomes negative 2x squared e to the negative 2x. So it just kind of joins this kerfluffle right here. The second term stays the same because I didn't multiply anything into it. Since this is as expanded as I can go, I now look for common factors. Is there anything that both of these terms share? 2x e to the negative 2x. All of them have that, or both of these terms have that. So I'm going to take a 2x e to the negative 2x out of each of these. What I'm left with then is the negative 1 from here and the x, plus all of this came out, so I'm just left with the 1. So I now have 2x e to the negative 2x times the quantity negative x plus 1. So I just pulled out that common factor and put it out front. Since this is all being multiplied together, I can break it apart and set each part equal to 0 and find my zeros that way. So clearly, what's inside the parentheses is one of my factors and will get set equal to 0. What's out front is a little bit different. Because it's two things multiplied together, I actually need to separate it and think about each of them individually. So the first portion I'm going to think about is 2x. That can definitely equal 0 at some point, correct? So I set it equal to 0 and I solve. But what about, make sure I get a different color, this e to the negative 2x there? Will that ever equal 0? No, because even if I get a 0 in my exponent, my answer is still going to be 1. The only way to get a 0 here would be to have a 0 as an e, and e is a constant, so that can't happen. So I do not have to consider this when I'm thinking about my zeros, because it will never equal 0. So my zeros are only going to be coming from these other factors that do not involve an e. So I solve each of those out, and then those become my zero. So over here I get x equals 0, because divide each side by 2, 0 divided by 2 is still 0. On this one I subtract 1 across and divide by a negative 1, and I get x equals 1. So my two zeros are 0 and 1. And I would put them in our nice, pretty curly brackets. And then I'm finished. Any major issues with that? Okay, I do want you guys to have time to work on your homework, so I'm going to stop here. There are, of course, some additional, at least one additional example in the notes if you'd like to look at it and work through it. It's a calculator one, so it's really just a practice, and then finding an intersection point to answer the question. There's not a question like that on your homework, though, because we're going to learn a trick for it later.